In our previous session, we discussed about flame photometry. So, how to determine the concentration of, or how to determine the concentration of lithium, potassium, sodium, etc. So, this is similar to flame photometry, but somewhat different. So, how it is different from flame photometry? Let us see. So, in both the cases, whether it is flame photometry or atomic absorption spectroscopy, we are going to subject the sample to flame. So both are subjected to flame and the light emitted is detected. Depending upon the transmitted light or emitted light, we are going to estimate the concentration of the particular substance present, but in a different way. So how atomic absorption spectroscopy is different from flame photometry, we'll discuss. And what is atomic absorption spectroscopy also, let us see. The main principle in the atomic absorption spectroscopy is that the amount of light which is absorbed is determined by, because the absorption of the light or the absorbed light is directly proportional to the concentration of the element which is present in the element or elements which are present in the sample. This is a simple principle. We'll see what is the theory behind this. So in the flame photometry, what are we going to do? We're going to take an element or the sample. We're going to ignite it or subject it to the flame. So by absorbing the heat energy, the metal will get excited and go to the higher energy level. So since the higher energy level is not stable, it will come back to the lower energy level. So while coming back to the lower energy level, what happens? The metal will liberate. The metal will liberate some amount of energy. While liberating, when metal liberates some amount of energy, that will come in the visible radiation. So it is liberating energy. It might be in the form of heat, it might be in the form of light. So if it forms in visible energy, that we are going to measure, that is in the flame photometry. So even here also we are going to subject the sample to the flame, but we are not, the metals which are going to the excited state, we are not worried. But even though when we are subjecting the sample for the flame, there are some metals which will not go to excited state. We are concerned about that. Let us see what will happen. We are going to take a solution which is having mixture of metal species, and we are going to introduce that to the flame. So the solvent metals will get evaporated and leaving behind the metal species. So what will happen? Some of the atoms can be raised to the higher energy level, and when it goes to higher energy level, there is the excited state, and come back to the lower energy level, it liberates some energy and it will be in the UV visible radiation that can be measured by flame photometer. So the other metals, there will be some large amount of metal atoms which remains in non-emitting ground state. It will be in the ground state only. So what will happen? This is having a special feature. So that is, the ground state atoms of particular element will accept the light radiation of a specific resonance wavelength. So this type of metal, when a light of this wavelength passes through the flame, part of light will be absorbed. So we are going to pass some amount of light. So what will happen? Part of the light will be absorbed, and remaining, and this light which is absorbed will be proportional to the intensity of the atoms, or that is a concentration of the atoms present in the flame. So by measuring the intensity of the light which is emitted by the flame, we can find out how much amount of the concentration of the metal are present here. So we are going to pass the light, so the some amount of light will be absorbed. Amount of light absorbed is directly proportional to the concentration of the atoms present here, right? So the emitted light intensity is measured. By measuring that, we can find out the concentration. So how is it done? We'll see. So what are the apparatus required? We'll see. So the apparatus required are radiant source, atomizer, monochromator, lenses, detectors, and we also need halo cathode lamp. So let us see what are these uses. What is the radiant source? So radiant source is nothing a hydrogen lamp used as continuous source of radiation. So for supplying radiation, we are going to use radiant source. Atomizer, it is having a similar purpose as that of flame photometer, but still. So this atomizer is generally burners used to break the liquid sample into droplets, and finally in this process the sample, whichever sample you are going to take, it will be converted into fine atoms. That is the main purpose of atomizer. So monochromator, it might be you're going to use gratings or going to use prisms. The purpose is to pass through to get a monochromatic light. So what is monochromatic light? A single wavelength light. So lenses and slits in order to get a spectral line if the element has a simple line spectrum. So detectors, you know very well. So detect which light it is. So next, the simple flow chart, how the experiment will go through. So you're going to have a sample flow here. It will go to the mixing chamber as usual in your flame photometer, where the the sample will get mixed with the air and it will go to the flame there. So from before it enters the flame, when it enters the flame, you have a halo cathode lamp. So what is this halo cathode lamp? This halo cathode lamp, it is nothing but a hydrogen lamp. It is a halo cathode lamp. So a halo cathode lamp emits more than one composite line for each element. So it will have a one spectral line for each element. Are going to emit different spectral line. So now we have a more higher version of cathode lamp which can emit more than one spectral line. So then you're going to monochromatize it. So most of lines are non-absorbing lines because they involve transition more than from ground state. So the most intense absorption line is selected to provide maximum intensity. So this halo cathode lamp is nothing but the hydrogen lamp. So from that light will come, it passes to the flame. Okay, so where you're going to send your sample. So there atomic absorption occurs in that flame. So there you'll have a slit. So the monochromatic light, whatever light it is emitted after the concentration. So if you have some 8 or 2 ppm, some amount of light will be absorbed, right, by the 2 ppm copper. For instance, let us consider 2 ppm copper. 2 ppm copper will absorb some amount of light. So that light will be gone. You're going to, that is, it should match, the resonance should match, copper resonance and the light which you are passing should match. So that will be monochromatized there and it will be sent into the detector. So that signals will be converted into the digital number in the device. That it might be your LCD display or system or whatever it is. So that is how it is done. So let us see what is the procedure. So we're going to take, first the meter will be adjusted to 0 absorbance or 100%. Absorbance will be 0. So blank solution. Okay. And the 100% transparency will be there. Okay. That is, since absorbance is 0, whatever light you're going to pass, entire light will go, right. Therefore 100% transmittance. So we're going to take 2, 4, 6, 8 and 10 ppm of, for example, let us take copper. 2, 4, 6, 8 ppm of copper solution. We're going to spray and we're going to make a calibration curve. We're going to take a sample. Even that sample also will be exposed to the flame and the absorption will be measured. So we're going to plot a calibration curve. From the calibration curve, we're going to determine the concentration of the copper present in the unknown solution. So let us see how the calibration curve looks like. This is the calibration curve looks like. So the x-axis is the concentration of copper, since you have taken the copper as example. Y-axis is the absorption. So for sample, we have only the concentration. So we have only the absorption for the sample. We don't have the concentration. From the y-axis, where the concentration comes for the this one test solution, we're going to plot there until we're going to draw a parallel line until it touches the curve. Once it touches the curve, we're going to draw a perpendicular. So to the x-axis, whatever value comes here, that is the concentration of the sample or the test solution given. So this is how we're going to determine the concentration of an unknown using atomic absorption spectroscopy. So now let us see what are the advantages and applications of atomic absorption spectroscopy. Applications of atomic absorption spectroscopy, it is mainly used in quantitative analysis. So quantitative means amount. Quality, you know, to find out whether this chloride is present or carbonate is present, etc. Quantity means how much amount of chloride is present. So for instance, you have taken the copper as example, right? So how much amount of copper is present. So to find out that, we're going to do that is quantitative, how much. Next, disadvantages. So this technique cannot be used for vanadium, silicon, molybdenum, aluminum, because these gives their respective oxides in flame. So when expose aluminum to flame, it gives aluminum oxide, tin oxide, molybdenum oxide, vanadium oxide, etc. So in aqueous solution, the anion effect affects the signal to a noticeable degree. Therefore, anions cannot be detected. The separate lamp, as I told you, hydrogen lamp. So your cathode halo lamp, you're supposed to have a separate for each and every metal. You're supposed to have a different spectral line. But now, anyhow, because of recent development in technology, it is overcome. The difficulty is overcome. So this is about applications and disadvantages of atomic absorption spectroscopy. So thank you.